In chemistry and material science, we are moving away from manual trial and error in the lab. But today, researchers are using machine learning to predict molecular behaviors and discover entirely new materials in seconds. This transition is supported by open-source hubs, like the awesome Materials and Chemistry Datasets repository. This diagram shows the ecosystem's scale, terabytes of data formats like SMILES, HDF5, and JSON, pouring into public access. But there is a bottleneck. As the funnel clogs up, having massive amounts of data is useless if the type is wrong. Feed the wrong data modality into your architecture, and you can derail a research project before it even begins. Finding the right repository involves matching the data's specific modality directly to your machine learning objective. To make this practical, let's look at 3 distinct profiles in this space: the ML interatomic potential builder, the LLM developer, and the applied chemist. Each of these researchers requires a different category of data to hit their goals. A dataset that helps a language model might actually hinder an interatomic potential model. We've built a step-by-step framework to help you select the exact category of data you need, based on the downstream outcome you're trying to produce. If you start downloading without identifying your core bottleneck first, you risk spending a large portion of your compute budget training on the wrong repository. Let's start with the simulation route. If your team is building machine learning interatomic potentials, or MLIPs, your goal is to replace expensive, slow quantum simulations with fast AI approximations. To do that, you'll be looking at massive computational repositories like OSUML25 or MS25. Look at this matrix of generated molecular lattices. To train an MLIP, you need to feed it tens of millions of these perfect, dispersion-inclusive, density functional theory relaxation trajectories. When it works, you get highly accurate, equivariant models. As the counter here shows, you can predict physical forces and energy states at fast computational speeds. But there is a trade-off: simulation bias. Watch what happens when we introduce a jagged external variable to this perfect matrix. Because the training data was perfectly simulated in a vacuum, it fails to account for real-world laboratory noise or complex macroscopic environments. Simulated data provides the scale needed to train physics models, but it operates in a vacuum, separated from the messy reality of the physical lab. That brings us to the second pathway, the physical reality route. This is for the applied chemist whose job is to predict actual physical outcomes, like whether a liquid will crystallize, what the synthesis yields will actually be, or how a battery will perform. You'll pull from different sources here, like Big Sol DB for experimental solubility values, or the Catacall benchmark for transient flow data. This scatterplot shows the input you're working with. Instead of theoretical math, you are training on curated, ground-truth laboratory measurements. The data points are sparse and irregular. The payoff is practical accuracy. By mapping these actual yields, the trend line isolates a successful synthesis zone. You can finally predict whether a compound will actually dissolve in a specific solvent on a real laboratory bench. The catch is the manual friction. Experimental data is notoriously messy. Look at these missing data gaps and null errors across our trend line. Before your model can ingest any of this, your team will have to spend time pre-processing, filtering, and deduplicating the files. Experimental data forces your models to confront reality, but the high data tax required to clean it makes this a labor-intensive route to scale. Our third pathway is the generalist route. This is for the AI engineers developing domain-specific large language models for chemistry. To build these, you need instruction datasets, collections like the ChemDFM, the MAT instructions database, or the MUL-TextNet repository. The workflow involves fine-tuning base LLMs on millions of literature-mined text-to-molecule pairs, alongside curated Q&A datasets. If executed correctly, you create an agentic AI. You get an interface like this, where a model can engage in scientific reasoning, design experiments, and hold interactive dialogue with your research team. But these models often suffer from geometric blindness. In this diagram, the text model correctly names a complex molecule, but when it generates the 3D wireframe on the right, the structure collapses into a physically impossible mess. Watch the spatial coordinates fluctuating in red. LLMs typically lack an understanding of precise 3D spatial geometry. They excel at identifying category patterns from text, but they are poor at structural physics. Chemical LLMs are masters of literature retrieval, but trusting a text-based model to handle structural physics or spatial reasoning can lead to significant physical errors. There is no single dataset that solves every problem in chemistry. The value of the data you download is dependent on the specific architecture of the model you intend to build. To replace quantum simulations, follow this branch to computational databases like OMC25 or the Materials Project. Applied chemists follow the second branch to experimental databases like CRIPT or the Battery Imaging Library. For foundation models, the third points to LLM corpora like ChemBench. Avoiding a compute failure comes down to matching your downstream goal to the correct starting node on this matrix. Advanced users can overcome geometric blindness by pairing the reasoning power of LLMs with external computational physics calculators. Open access hubs support this work by democratizing hundreds of terabytes of data for researchers globally. Navigating these open-source ecosystems allows organizations to shift their focus from basic data ingestion toward engineering targeted scientific breakthroughs.